Hey Sam, how are you?
Good. How are you?
Doing good as well. Thank you. All right.
Awesome.
Have you done stream before?
Have I done what?
Have you done a live stream before? Like, is this your first one, or have you done this multiple times?
I've done it once,
Well, then
and then
once.
this
Okay,
is
cool.
my second time. What about you?
This is my first one, so
Oh,
I'm gonna
awesome.
have to look. I'm gonna have to look for you. Look to you for some guidance here. So, I was looking at the slides. These questions are like pretty long. So, do we go until the hour is up, or do we go until we finish all the questions?
So we go until the hour is up. Sometimes we don't get through all of them, but we try to get through as many as possible. Yeah.
Got it. Okay. And how frequent do you like call on somebody? So like is it often that you read chat and like respond to people, or do you just
So
usually just go through it?
yeah, so we don't actually call on many students, um, but instead we look at the chat and it's just the same as a normal class. So we'll pull from the chat. Yeah, we don't call on as many students. So we don't call on students.
Well, okay, yeah, that's good. And yeah, so we'll go through. Let me think if there's anything else. I
Okay,
think that's pretty
awesome.
much it. Yeah, I think that's good. Okay.
And
We
then
didn't check chat relay at all, so I was wondering if we had to
yes.
check that.
I think we do. Yes, we should do that. Mhm.
Oh, and will Professor Lowe be here for he'll be here for like a little bit in the beginning, right?
Yes,
So,
just to
okay.
introduce some things.
How do we
Okay,
check
it
chat
says
relay?
Mark is in the waiting room. I don't know if he's in the same one as we are.
Oh, yeah, he might be in the other one, right?
Mhm. Let me check with him.
Is he there? I don't know. Let me ask. Oh wait, I'll send we're in this link. Be
Oh wait, okay, wait, never mind. We don't bring in chat relay. That's brought into the public Zoom room. I think that already happened, so we're good
okay.
there. Um, awesome. Hello,
Oh,
Professor
hello,
Lowe.
Professor Lowe.
Oh wait, I see a message in the
Hey guys, hi
chat.
guys.
Okay, chat is good. All right, awesome.
Okay, and the chat's here.
Cool.
Okay, this is working. I'm gonna go send reminders to everyone. I'm not sure that the reminders were sent. That's good. Reminders meeting to all the people who registered for the live self.
And then really quick, I'm just gonna go ahead, put an icebreaker on the screen so that they have something to answer. So where are you from? That's our standard one.
Yeah, you guys are awesome. By the way, I will not introduce you each individually, but I'll introduce you both together. And then each of you, do you have your bio?
Yes, let me go ahead and paste this in there. Jeff, do you want to get yours up and then I'll go ahead and pull
Yeah.
mine up? Okay, awesome
Cool.
sauce.
Um, yeah, so you're gonna introduce me and I'll introduce you, right?
That's correct, yeah.
Good,
Just
okay.
like
Yeah,
in a
and
normal
I
class.
usually go with the first, I guess, okay, I can pass it to Sam first then. I'll do that.
Mhm.
Okay,
Okay.
awesome. Okay,
Hi, everybody. How are you? Well, welcome to our live solve. First, I want to double check if the sound is working. If you can hear us, could you please send a message to chat relay saying what color my hair is? That way I know that you actually can hear what I'm saying. So the way you send messages in this whole live solve is you choose chat relay as who to send to. Okay, great, great, great. That means that the sound works. Right. So first of all, welcome everyone. And you notice that people are having a whole lot of fun typing things in. The way that you talk in our class is that you send messages to chat relay. Don't send them to everyone. And then you'll see that the messages appear on screen. We actually have a moderator team, which also helps to screen them before they show up. By the way, you might notice some stars. That means that we like your message. And if you say things that are not so nice, unfortunately, you'll get the opposite of stars, which will make you not able to talk anymore. So don't do that. Okay, well, with that, let's do a little bit of introduction of what we're doing today. We're going to be doing some math. This is an official collaboration together with Math League. How many of you played with their contests? Already, you can talk into the chat relay if you want. How many of you participated in their contest? Because what we're doing here, good, me, I love it. So what we're doing here is we're going over the problems in the most recent round. We love to collaborate with Math League because they have 6 qualifying rounds every year, and that gives us all a chance to play with some interesting math problems every month. Now, Math League is kind of unique in the fact that they have these 6 pretty good contests which are running every month. And if you don't think you'll do it, I strongly recommend you to. And who knows, maybe after this, you'll decide to join the next round. By the way, I'm Po Shan Lo, so this is the YouTube channel that you're on. Officially, I'm a math professor at Carnegie Mellon. I'm actually back at home in Pittsburgh because I just had to come home to grade the final exams. But I'm actually not final exams, the midterm exams for the class I'm teaching at the university. I do not have a green screen. This is actually my house. See, I'm not green here. But anyway, I myself will not be doing the math problems here though, because we have 2 incredible people who are going to take over. And they are Sam and Jeff. They have been teaching on our live platform for quite a while. And I think you'll be in terrific hands. They're also far more interesting than I am with better visual effects. With that, I'm going to pass it off to Sam to start introducing Jeff and so on. And I wish you all a great math time.
Awesome. Thank you so much, Professor Lowe, for that intro. We are so happy to be here. So I'm going to go ahead and introduce my super awesome teaching assistant. So here I'm with Jeff today, and Jeff is super cool because he's really, really awesome at math, but he's also a really interesting person. So Jeff is a 2-time AIME qualifier, and if you don't know what the AIME is, that is the American Invitational Mathematics Examination, and it's a very big exam. He is also a National Mu Alpha Theta Award winner, and he teaches math for his school team. In his free time, he enjoys playing violin, which is so awesome. So yeah, give a very warm welcome to Jeff. We are so excited that he's here with us today.
Yeah, thank you so much, Sam, for giving such a warm introduction. Great to meet all of you. I'm so excited to go through these questions with you and to journey through this math. So, now to introduce Sam. Sam is also such an amazing person. So, Sam has been competing in math competitions since the 3rd grade, placing at the top 5 in the Georgia State Math Counts competition and qualifying for the AIME twice. Both incredibly amazing accomplishments. Sam also volunteers for the Math and AI for Girls competition and is an officer for our school's math team. And in her free time, she loves debate, reading books, and listening to classical rock. So let's give Sam a warm welcome.
Thank you so much, Jeff. I really appreciate it. Okay, awesome. So I see a lot of you guys are already answering the question on our screens, which is where are you from? If you haven't done so already, definitely go ahead, type your answers in chat relay. And I know we have lots of people from all over the world today, so we're really, really excited. We have lots of people from the US too, which is really great. Oh, I see Daniel is from Romania. Sharanjit is also from America. Oh, Leo is from Texas. Nada from India. Wow, so many different places. We are so excited, like people from all over the world. Anyone in oh wow, we have a couple of Georgians too. I'm from Georgia as well. That's really cool. For anyone in the US, if you are missing the Super Bowl to be here, that is so awesome. Thank you so much for doing some math with us instead of watching some football. We'll probably get you out before the halftime. So if you're looking forward to that, definitely we'll get you out before then. So many
Sounds
people from
great.
Georgia. That's cool.
Oh, yeah. Yeah. Is anyone here from Florida? I'm from Florida. Are there any Floridians here?
Oh,
Oh,
Maxwell
Maxwell.
is from Florida. That's so
All right, fellow
awesome.
Floridian. All right. Are we ready
Okay,
to jump in, Sam?
yeah,
Ready?
let's go ahead. Let's get into some problems.
All right.
So we're gonna go through the odd problems today, but there's gonna be lots of fun and difficult problems. So yeah, hopefully you guys will learn something new. So yeah, let's go ahead and jump in.
All right. Let me right in. Question 1 of this year's Math League sprint round. So we're going to do sprint first and target after. What is the unit digit of 17 to the 2025th power?
Anyone got any ideas or answers in the chat? You guys are totally welcome to put your thoughts, answers, solutions in the chat, and we will do our best to highlight those who say anything.
All right,
Awesome. So I see a lot of people saying 7 and 1, and then I also see a lot of people talking about patterns. So Jeff, do you want to go into this idea of patterns? Because I think that's really interesting.
yeah. So when we're looking at questions where we solve for the units digit of a number to some really big power, you must wonder if there's a pattern, right? Because the power is 2025. 2025 is a nice number. It's like the year, but it's also a really big number. I would not want to find this number, so there's probably a nice pattern. There's something important when you're doing units digits calculations. It's that you only care about taking this units digit to some power. So when you multiply any two numbers together, the units digit of the product is the same as the units digit of just the units digit multiplied. So for example, if I want to find the units digit of 17 times 17, you don't actually have to do 17 times 17. You can just do 7 times 7. It's 49. And whatever ends up below here, there's always a zero in the tens place or even more zeros. So the final answer will have a 9 in the last place and something random here. We don't really care what that is. What is 17 to the 2025th? Let's see, there's probably a pattern. I see people in chat are saying there's a nice pattern. So 17 times 17 ends with a 9. We already got that. So we start with 17 to the first power ends with a 7. 17 to the second power ends with a 9. What about third power? What do you think? Well, we can do 9 times 17. But we don't actually have to do 9 times 17. We can just do 9 times 7. 9 times 7 is 63. So ends with a 3. And for our final calculation, 3 times 7 is 21. And then a 1. And if we do it again, we go back up to 7. So there's a nice pattern, actually. It seems like 17 to the first, we go 7, and then 9, and then 3, then 1, and then we go back up to 7, 9, 3, 1. Now we have to just figure out which one it lands on. What do you think, Sam?
Yeah, I think it was a really good job. We found a pattern, and now we just got to find where does our pattern end. So, with 2025, an interesting thing to note is that we can look at the remainders for each power. So, for example, when I have 17 to the power of 1, I end with a 7. And then if I also have 17 to the power of 5, I once again end with a 7. So we can see that like anything that's divided by 4 and has a remainder of 1, I'm ending with a 7. So in this case, when we do 2025 and we divide that by 4, what kind of remainder do we get? Yeah, I see Shrish and Aaron saying we get a remainder of 1, and that is absolutely correct. Notice how I really don't care about what my quotient is. Like, that's not relevant to the question. I just care about what my remainder is. So my remainder is 1. And from the chart over here, if we have a remainder of 1, our units digit is just 7 to the power of 1, which is 7. So yeah, that's how we find out what this units digit is. I see Jeff has some really interesting notation on his screen. Jeff, do you want to explain that for us?
Yeah. So one really nice way to write out remainders is using mod notation. So mod just means like the remainder when you divide by that number. So 1 mod 4, it's written like the number 1, mod, and then 4. This means that whatever number you divide by 4, you get a remainder of 1. So right here I wrote 2024. Three horizontal lines means congruent too. It basically means equals. 2024 equals 1 mod 4. That means that when I divide 2025 by 4, I get a remainder of 1. And if we look at this pattern right here, we can see that if you take the power of 17, divide by 4, and whatever remainder you get, that's kind of what number you have in the unit digit. So if you divide whatever power we have, in this case 2025, by 4, you get remainder 1. You should look at this horizontal row, and you get 7 as your final answer.
Yeah. I saw Leo put in the chat that mod is basically equal to the remainder, and that's exactly right. Modular arithmetic is a way of working with remainders. So if you guys have never seen that notation before, it's totally okay. It's not very common in school, but it's very, very popular in competition math. So it's just a way to denote some remainders.
Yeah. So
Awesome.
we learn a pattern and we learn a new notation. So I think the answer is 7. Want to check our
Yeah,
answer, Sam?
let's check it out.
Let's check it out. All right. Ta-da! And the answer is
Awesome.
indeed 7. Yeah.
Okay, perfect. Okay, let's move on to question number 3. Oh, this is a big one.
All right. You want to give it a read, Sam?
All right. I don't think I'm going to read the entire paragraph. I'm going to try to summarize this for y'all. So Troy has a bag with 8 red marbles and 6 purple marbles and some blue and green marbles. And the probability that a randomly chosen marble from the bag is red is 2/5. And there is 1 marble of each color in the bag, and we want to find out how many possible numbers of green marbles there are. So notice that the question isn't just asking like how many green marbles there are, they're asking how many different possibilities of green marbles there are. Okay, so let's take a look. I see a lot of people saying 5 and a couple of 3s as well. So let's see if we can settle that debate. All right, Jeff, how would you start this question?
I think let's start by thinking about what the meaning of probability is. We're given that the probability of choosing a random marble and it being red is 2 and 5. What probability, the numerator in probability, it's like the number of cases that this event happens. Denominator is like how many total cases there are. So in this case, the 2 on top would mean that there are like essentially like 2 red marbles. Obviously, it could be some multiple of 2 because the fraction could be simplified. And then the 5 on the bottom means there's like 5 total marbles. So 2 and 5 means that for every 5 total marbles in the bag, we have 2 red marbles. We can actually use this to find the total number of marbles. If we know that there are 2 red marbles for every 5 total marbles, and that we know there are 8 red marbles, we can just scale this fraction by 4 on the top and on the bottom. So 2/5 multiplied by 4 over 4 gives you 8 over 20. So this means that since we have 8 red marbles, there must be 20 total marbles. We seem to be getting somewhere. What do you think, Sam?
Yeah, I think this is a great approach. So once again, I just want to reiterate, our total probability is 2/5, and the number of red marbles that we have is 8. So that means our total number of marbles has to be, we can do this as, hold on, I'll actually write it like this. Total is equal to 5 times red over 2. And so that is going to be 20 total marbles. So we know that there's 20 total marbles. So let's go see what the question is asking us to do. We want to find out how many green marbles there are. And there's also a whole number of blue marbles and green marbles. So right now we know that there's 8 red marbles and 6 purple marbles. So right now we have 14 marbles. And then we have 6 marbles that must be split up between green and blue. Okay, so how do you guys think we can split marbles between green and blue? Remember, there has to be 1 marble of each green and blue. So we can't have 0 green and 6 blue. We have to have at least 1 green and at least 1 blue. I know one way I can think of is maybe we have like 1 green. Actually, I'll write this in a different color. We can have 1 green and 5 blue. What other possibilities can you guys think of? Oh, I see Rashawn saying 2, 4. And then Rashawn also saying 3, 3. Okay, that's perfect. Shrish says 2, 4 as well. Oh, I wrote 2, 2. See, 2, 4, and 3, 3. All right, what about the other way? Can we have 4 green marbles and 2 red and 2 blue marbles? Is that possible? What do you guys think? Yes. Okay, Ryan
Yes.
says
Okay.
yes. Yeah, awesome. So we can have 4 green, 2 blue. And then similarly, we can also have 5 green and 1 blue. So how many possibilities is that in total, Jeff?
Yeah, so let's just count. If you count the ordered pairs, there are 5 total ordered pairs. So I think the final answer should be 5. One
Okay,
quick way we can
awesome.
count this, well, just one thing to add. A quick way we could have counted this is we can think about the maximum number of green and the minimum number of green marbles we could have. So we could have the highest number of green we could have is 5 because you have to have at least 1 blue. The smallest number of green you can have is 1 because must have at least 1 green. So from 1 to 5, there are 5 numbers inclusive. So therefore, the answer should be 5.
Yeah, let's check it out. Okay, and we're right once again. Awesome. This is great. Okay, hopefully that question makes sense for those of you guys who said 3. Remember, we also have to count like the ways that the blue and the order pairs switch, basically. We have to count those ways as well because those are distinct possibilities. So hopefully that clears that up a little bit. All right, let's move on to question number 5.
Ooh, geometry. Interesting.
You want to give this one a
Rhombus.
read, Jeff?
Yeah.
Awesome.
Rhombus ABCD has side length 5 and a diagonal of length 6. What is its area? All right. Well, in geometry, as my teacher always says, you always start by drawing the picture. So let's draw the picture. Okay, we have a rhombus.
Okay, you're gonna draw the diamond one as well. All right, that's what I'm gonna do too, because there's
Oh,
sometimes multiple ways to draw it. I want us to make sure we're drawing the same kind of
oh,
diagram.
okay. Oh, do you draw it sideways sometimes with
No,
like
I
the
draw mine like this too, but I didn't know if you drew yours like this, you know? So
Oh,
I just wanted to make sure.
actually, I don't know anybody who draws it that way.
I know,
Interesting.
because it's like confusing. I feel like this is the easiest way to look at it.
Yeah. All right.
Also, okay. Yeah, anytime you have geometry, always start with diagrams. Really helps you visualize the problem, get a grasp on it. So yeah.
All right. My rhombus is slightly suspicious, but it should be okay. As they say in math, it's not about art, it's about having a slightly workable picture. Okay. 5, 5, 5, and 5. We have four side lengths of all fives, because by definition, a rhombus has equal side lengths, so that's a good start. And we have a diagonal of length 6, so we can call either of these 6. Although if you call the wrong one 6, it makes it a little bit harder because you might guess the picture is like the other diagonal is either bigger or smaller, and you could guess wrong. But let's just take a gamble. And I think Sam chose the middle one, so I'm going to choose the middle one as well. Let's call that 6. Okay. Any ideas on how we can find the area of a rhombus? Oh, I see some people saying 30, some 24s. Oh, Francis says split into two triangles. Okay, that's a good idea. We've already have two triangles here. Can we find the areas of these triangles? Well, Pink says we could use Heron's formula. Oh, Heron's formula is a good idea as well. We can do Heron's formula because we have the three side lengths of all these triangles. But notice they're also
Oh, sorry.
isosceles,
Go ahead.
right? They're also
Yeah.
isosceles. Maybe we can do that, right? What were you going to say, Sam?
I was just gonna say, Hertz formula is a little complicated, and there's probably an easier way to do this. And like Jeff said, this is an isosceles triangle, so that gives us a very nice property to use in this case. So I wouldn't go with the Heron's formula route. If you're not familiar with what Heron's formula is, that's totally okay. It's actually not necessary in this problem. So yeah, Jeff, why do you think it's important that we have an isosceles triangle? What could we do instead?
Well, isosceles triangles are really nice, right? You can do a lot of things with isosceles triangles, but finding area of isosceles triangles is generally pretty easy because you can find the height with Pythagorean theorem. If you drop an altitude to the 6, this is 90 degrees. And since these two triangles are like symmetric, it splits the 6 into 3 and 3. So you have a right triangle of hypotenuse 5 and a base of 3. What's the height? It seems like a very familiar triangle.
Oh, Mada says 4. Oh my gosh, so many people say 4. Okay, that's awesome, you guys. Yeah, absolutely. It is definitely 4. So for those of you guys who are not familiar with this triangle, this is a very, very famous right triangle, and it's derived from the Pythagorean theorem. So the 3, 4, 5 triangle is one that pops up all the time in competition math. So we highly recommend that you guys remember it. If you don't know what the Pythagorean theorem is, just to give you guys the formula, it is a squared plus b squared is equal to c squared. And so in this case, A and B are the legs of our right triangle. So that means it's going to be this value over here, and then this value over here. And then C is our hypotenuse. So it's this value up here, the 5. And that's how you can find the lengths of right triangles. Right.
Yeah,
So
good explanation. So,
what do we do now, Jeff?
okay, what do we do? So we have the height of a triangle, we have the base. We can find this area pretty easily, right? It's like 6 times 4 over 2. That's the area of one triangle. We're trying to find the area of two triangles, so it's just 6 times 4 over 2 times 2. Then the answer should be 6 times 4, so that's 24. So the area should be equal to 24. So I guess that gives you a very nice formula, right? It's like 4 is like half the diagonal, so 6 times 4 is kind of like one diagonal times another diagonal over 2, so you get 24. Very nice.
Yeah. Oh, wow. Hold on, I just want to highlight this really awesome solution, or actually this awesome hint that we have in the chat from one of our moderators about what a rhombus is like and kind of the geometry there. So rhombuses are really nice because we're able to get lots of fun isosceles triangles from it. So we like rhombuses. Rhombi, I don't know, however you say it.
Rhombuses. All
Okay,
right.
awesome. Let's see if our answer is correct. Yay, we're right once again. Wow, we've got a streak of 3 so far. Let's see if we can keep this up for the rest of class. Okay.
Right. Ooh, number 7, another geometry question. You want to take this
Oh
one,
my
Sam?
goodness gracious. Why am I getting the massive paragraphs? Okay, let's see. Rectangle ABCD has side lengths AB equal to 12 and BC equal to 5. And then we've got points E and F that are midpoints of AB and CD. And we have a point G that is the midpoint of segment EF. And we want to find the area of quadrilateral AEGD. So this is a lot of points and lines and things. So once again, since it's a geometry question, we should totally start with a diagram. And Jeff is already like 5 steps ahead of me, so I'm gonna catch up.
All right. I think it also helps to label the vertices with the like actual letters too. I think it's very confusing if you don't do this. So like if you call like A, B, C, D, if you just label it, it's very helpful. All right, AB is 12, BC is 5. Okay, and then we have more points. Okay, there's a lot of points. So E is here, F is here, G is the midpoint of EF. Okay, so G is like kind of, it seems like G is the very middle of the rectangle, right?
I think so.
Okay, and we want to know the area of quadrilateral AEGD. Okay, so AEGD is here. It's kind of a weird shape. Let me highlight this. So AEGD is like half the rectangle and then minus this little bit here.
Actually, I think that's a good way of also maybe finding that area.
Hmm. Yeah. When I solve geometry questions, I think it's usually good to have a kind of a game plan of what you're planning on doing. So I think one idea we can have here is find the area of half of the rectangle, and then we can subtract out this triangle right here, triangle DGF. And if you subtract that, you'll get the area of this quadrilateral. Maybe there's some other way to do this. I see this is a trapezoid, right? This is a trapezoid because you have some parallel sides. So maybe you can just directly use trapezoid area formula, and that works as well.
Yeah, and I see that Peng has already went ahead and put the trapezoid formula in the chat. So I think maybe we could try the trapezoid formula, and then we can also check with like the first method you suggested with subtracting, just to see if our answer is correct.
Yeah, good idea.
Awesome.
So, okay, trapezoid area. So we have to have the base lengths, or like the average of the base lengths, and we need the height. So the height here should be, the height's actually horizontal in this case. So the height's like this, from like A to the line EF. And that should be 6, because it should be half of AB. What are the bases?
So we know that AD is 5 because that's parallel. So over here we've got AD is 5. Oh, there we go. There we go. And then EG, because G is the midpoint of EF and EF is parallel to AD. So first of all, EF is going to be 5, and then EG is going to be half of that since G is the midpoint of EF. So that means EG is going to be 5 over 2. Perfect. Now where do we go from here?
Hmm. The formula for an area of a trapezoid is the average of the bases multiplied by the height. So we need to average 5 and 5 halves. So we add 5 plus 5 over 2, and then divide by 2, and multiply that by 6. I actually like to write out the whole formula at once and then simplify later because sometimes you can save steps, save some computation. So in this case, we can actually just cancel the divide by 2 and the 6 and get a 3, which saves us some time in computation. So now it's just 5 plus 5 halves all times 3. 5 plus 5 halves is 15 over 2 times 3 gives you 45 over 2. And I also liked how Sam chose to use fractions for all these like answers. So we call EG 5 halves, not 2.5. I think it helps a little bit to go with fractions since the question is also asking for an answer as a common fraction and not a decimal.
Yeah, and for those of you putting mixed numbers in there, just be careful because sometimes mixed numbers can be a little misleading. So in general, heed to what the problem asks you to do. So if your problem asks you to write in a common fraction, use common fractions, not decimals or mixed numbers. Okay, awesome. So this is how you find the area using a trapezoid formula, which is really great, very efficient. So let's take a look at how to find the area of a trapezoid by taking the rectangle and then subtracting this right triangle over here. I also saw Nico said earlier, why don't we make a rectangle and then add the triangle? Actually, those two methods are very, very similar. There's just one small change. Nico, if you want to try to find that, that would be really cool. So I'm just going to go ahead and use the subtraction method. So first, we look at rectangle AEDF and the area of AEDF. By the way, I'm putting square brackets around my letters because that denotes area. So yeah. The area of rectangle AEDF or AEFD, I just said those vertices in the wrong order, is 6 times 5 or 30. And then we want to subtract the area of triangle DGF, and that is going to be 1/2 of 6 times 5. And so that's, oh wait, hold on, not 5, 5 over 2. And so that is going to be 15 over 2. So then I do 30 minus 15 over 2. And I once again get 45 over 2. So we know that since these answers are correct, we're like 99% confident that our actual final answer is correct. And to get that 1% extra confidence boost, we're going to go ahead and check our answers. So let's see. Jeff, are we right?
Let's see.
Yes, we are.
Yes,
Okay, now we are 100% sure we're right. This is awesome sauce. Okay. Perfect.
All right. Ready for question 9? All
Yeah.
right. Really flying through. Oh, whoa. Okay.
Oh, you guys
A
saw
short one.
nothing.
The decimal expansion of 11 factorial has n digits. What is n? Hmm. All right. Well, right after that, we can solve this question by writing out 11 factorial. I would not recommend that. I think writing out 11 factorial might be a little bit challenging. Is there a neat way we can do this question without writing all that out? Hmm. Okay, I see some people have some factorials memorized. Actually, that's actually pretty good to know. In competition, it helps to have like maybe 8 factorial or 9 factorial. Just memorize like one of the high factorials, and it's pretty easy to calculate with that. So that's one way we can do it. Is there a way we can do it a different way?
I do see some people saying, can they use calculators? And since this is the sprint round, we actually don't allow calculators. That's why this question is pretty difficult because you're not allowed to use a calculator to find out what 11 factorial is.
Yeah. Ooh, Thomas says estimate. Okay. Is there a way we can estimate this quickly? So 11 factorial is 1 by 2 by 3 by 4, and then all the way up to 11. Okay. I think with estimation, it helps to group them up into numbers that are close to 10. So because multiplying by 10 gives you one extra digit, right? Let's just try to group these products up into things that are like nines or like 99s, 101, like somewhere around 10. So we have a 10. We don't have to worry about the 10. We can put the 5 and the 2 together, right? Because 5 and 2 together make 10. That's another 10 right here. So we have, let's cross these out. We have a 10 and we have another 10. Cool. Anything else that are easy to group together?
I see a 9 and an 11, and that's 99, so that's pretty close to 100, so you can do that one.
Yeah. So this is like approximately 100. It's a little bit less, but it should be okay. Anything else? Hmm. 4 and 6 is 4 times 6 is 24. That's pretty close to 25. Maybe if we borrow a 4 from the 8 and do like 4 times 6, that's also around 100. We can do that as well.
Oh, wait, actually, maybe instead of 4 times 6 times 4, we could just do 3 times 4 times 8, and that gets us to 96, which is the same as what 4 times 6 times 4 is. And that way we're not splitting any numbers up.
Yeah, I like that. Okay, so 3 times 4 times 8, you get 96. It's like approximately 100 as well. Okay, so our final product is like a little bit less than 100. We just have to make sure that at the end we subtract a digit because it's like a little bit less than 100. So it's like one less digit. Okay, we're left with 1, 6, and 7. I don't think there's not much we can do with that. So let's just write 42. So we have 42 times 10 times 10 times two numbers a bit less than 100. Okay, so 10 times 10 is easy. These just add digits. Two numbers a bit less than 100 multiplied. 100 times 100 is 10,000. So then this product should be like a little bit less than 10,000. It should be like 9,000 and something. So whenever we multiply this, whatever this product is to our rest of the product, it'll add 4 digits instead of adding, or it'll add 3 digits instead of adding 4. It'll like be one less zero. So it should be 42 times 100 times, it's like a little bit less than 10,000. So let's just write this. All right. What do you think the answer is, Sam?
I think, hold on. Wait, I just want to make sure that we're both on the same page here. Okay, perfect. So I've got 42 million on my screen. Jeff, what do you have?
I've got that as well. I've got
Okay,
42 million.
perfect, perfect.
Okay.
So the answer, like Jeff said, is definitely like okay, not the answer, but 11 factorial is a little bit less than 42 million because we did a little bit of overestimation. So we rounded 99 to 100 and we rounded 96 to 100 as well. So because we rounded up, this 42 million over here is actually an overestimate, but it's not such a big overestimate that we have to count down a whole digit. We're kind of like maybe in that 42,000 range to that like maybe 38,000 range. So really we're still in that like not thousands. I keep saying thousands. I mean millions. So 42 million to 38 million, but we're still in that millions range. So I'm pretty confident in saying that our final answer is just going to be 8 digits because that's what I have over here. And Jeff, you seem to have the same as well. And also everyone in chat, including Nico, Ryan, lots of people, hold on, that's all I can see right now. Arnav, are saying 8 as well. So if our students agree, I think we're pretty confident that the answer is 8. You want to check?
Yeah, I agree. All right, let's give it a check.
Okay.
And our answer, it's indeed
Yay.
8. Yay. All right. Wow, we have a
Awesome.
we have a long streak going. Okay, let's keep that up. Question 11 now. Oh man, it seems like you're getting all the long ones today, Sam.
I know. Okay, this one isn't like that long though, so I feel a little better. But let's take a look. I'll try my best to summarize. So we've got two rectangles, and both of them have area of 30 and integer side lengths. The length of the longer side of one of the rectangles is twice the length of the shorter side of the other rectangle. And we want to find the sum of the perimeters of both rectangles. So what do you guys think? What can we do? Yeah, CC says this is another geometry problem. Seems like all the odd questions are geometry, which is really funny. But that's okay. Oh, Niranjana asks, what are integers? So integers are basically numbers without decimal. So they are both negative integers, positive integers, and then 0. So all of these numbers don't have decimals.
Yeah. So in this case, because it's geometry, we can kind of ignore the 0 and the negative parts. So integers will just be the 1, 2, 3, 4, 5, 6, and so on. It'll be all the numbers beyond that. All right. My first thought when I read this question is, okay, if two rectangles have area 30 and they both have integer side lengths, there's not that many rectangles that could be here, right? Because 30 only has so many factors. So we can probably write out all the rectangles and then just guess. That's what I'm thinking.
I
Okay.
think that's probably safe. Yeah, we can do that.
All right. So CC wrote it out. So there's 1 by 30, there's 2 by 15, 3 by 10, and 5 by, or yeah, let's do 5 by 6. And then there's actually technically 8, I guess, if you reverse these, right? But it should be okay. So let's see. The second line says the longer side, or the length of the longer side of one of the rectangles is twice the length of the shorter side of the other rectangles. So which two rectangles do you think satisfy that?
I see lots of answers, like final answers, but looking at intermediate steps. Okay, Francis says 1 and 30 and 2 and 15, and then Rashawn says 3 times 10 and 5 times 6. Oh, wow, okay. Now Selena says 1 and 30 doesn't work. All right, let's take a look. Let's see if 1 and 30 does not work and why. All right. Oh, okay. So remember that the question says the length of the longer side is twice the length of the shorter side of another rectangle. So if we look at 1 and 30 and 2 and 15, 2 is double 1, but both 1 and 2 are the shorter sides of the rectangle. So that means that 1 and 30 and 2 and 15 are not the right pair. So thanks, Salita, for pointing that out. And also Easton, I just saw Easton put that into the chat really. Okay, so that means we're left with the pair 310 and 56. So let's find our final answer. What is the perimeter of a rectangle with sides 3 and 10? Yeah, so, okay, thanks, Leo, and Trish, and AX. So it's just going to be 2 times 3 plus 10, which is 26. And then similarly for a rectangle with sides of 5 and 6, we have 2 times 5 plus 6, which is 2 times 11, or 22. And finally, adding those together, because our problem asks for the sum of both rectangles, we get 26 plus 22 is 48. And that is our final answer.
Yeah. All right. It's a pretty quick solve. Let's check our answer. And we're right again. Awesome,
Yay.
guys. Let's keep it up. Let's keep up the streak. Let's move on. Question number 13. Ooh, not geometry this time. Let n be an integer. Given the sum of the digits of n is 2024, what is the least possible value of the sum of the digits of n plus 1? Ooh, this seems pretty challenging. All right, we have some answers of 9. We have Ryan's as 1. What do you think this number looks like? If the digits sum to 2024, what would you make it? What would you make the number to where you add 1 and then minimize the sum? Okay. So I
Oh, I
see.
see some people using some notation we introduced earlier. I think it says you can consider mod 9. And for those of you who are still a little unfamiliar with what mod is, that's basically just remainder of 9. So you want to look at um, things with 9. Oh, and then Nico also says that most of the digits should be 9. Okay, that's very interesting. Jeff, do you want to break down why Nico might say that? Why should most of
Yeah.
the digits be 9?
So the current sum of the digits is 2024. Normally, if you add one to a number, the sum of its digits, it just goes up by one, right? Like if I add one to one, you get two. If I add one to 10, you get like 11. So the sum of the digits just go up one. But there's a special case where it doesn't go up, it goes down. And that's when you add one to a nine and it carries over to the next one. So like if I add one to nine, you get 10. And the sum of digits just went down eight then. So in this case, we want to have a number that ends with like as many nines as possible, and then like you add one, and like a chain reaction causes all of the ends to become zeros, and you'll have some number at the end. So it'll be like some number in the beginning, whatever number this is, we don't know, and then like nine, 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 and it's just like a ton of nines all the way down. So these will all be nines. Now the question is, what is this number in the beginning, and how many nines do we have? I think this is where we can use mod because we don't really actually care how many nines we have because however many nines there are, when we add one to it, these all become zeros, and the number that we have in front just gets a plus one to it, and the number in front plus one will be our final answer. So the number in front is whatever remainder we have of 2024 when we divide by 9. So 2024 mod 9.
Now, I want to ask a question. So I just wrote on my screen 2024 divided by 9, and I'm getting ready to do some long division. But here's the question. Do we really have to divide by 9? Oh, okay. AX says no. All right, good. Because I really didn't want to do this massive division with this massive number. So why do I not have to divide by 9? Like what can I do instead? Okay, AX says we can use the sum of the digits. That is absolutely right. So does Shrish. And also the 9. Awesome. Okay, so yeah, we can totally look at the sum of the digits. So why? Remember that the divisibility rule for 9 is that the sum of the digits must be divisible by 9. And if that sum is not divisible by 9, that's going to be your remainder, actually. So there is a nice, beautiful number 3 proof for this. And if you guys are interested, we definitely recommend you look it up. But for now, we're just going to use this fact. So the sum of the digits of 2024 is 2 plus 2 plus 4, and that's going to be 8. So 8 is obviously not divisible by 9. It's just 8. So our remainder when 2024 is divided by 9 is 8. And if you're not convinced of the sum of the digits trick, you are welcome to go ahead, use a calculator, or do some long division and check. But I'm sure you'll get a remainder of 8. So that means our first digit is 8. Now what? So we add 1. What happens then, Jeff?
Yeah, so let's add 1 to 8, followed by, I think chat says 224 nines. I'll believe you. I think we'll trust that answer. 224 nines is a lot of nines. When we add 1, like we said earlier, these all become zeros, and 8 goes up by 1. So our final answer should be 9, followed by a lot of zeros. But we don't care how what the zeros are. We're finding the sum of the digits. Sum of zeros is 0. So the final answer should just be this lonely 9 in the front, bringing our total to 9. All right.
Awesome. You're a much faster writer than me, so I was catching up. Okay, let's take a look. Are we correct? Yes, we are. Okay, awesome. So I think we're almost halfway there. Almost. All right, let's take a look at number 15. Oh, perfect. Okay, this is not a long paragraph question. Lots of equations though. That's okay. I can read equations. So we've got two numbers, x and y, that are not equal, and they satisfy the following equation. So x squared minus y squared over x minus y is equal to 100, and x squared plus y squared divided by x plus y is equal to 36. And we want to find out the product of x times y.
Hmm.
All right. Okay, so I am honestly not a fan of like these quadratics in the numerator. I kind of want to simplify them. So, oh wow, okay, Thomas literally just read my mind. The first equation can simplify to x plus y via the difference of two squares. Okay, let's take a look at that. That was just like you just read my mind, Thomas. That's awesome. Oh, serious, there's letters in math now. Yeah, I know there's letters, but it's okay. We'll make the letters fun. If you guys don't like x and y, think of it as like symbols, like fun symbols, fun fun characters to represent X and Y instead of letters. Okay, awesome.
Yeah, so difference of squares. I don't know if you guys heard of difference of squares before, but there are really nice ways to factor certain expressions, and difference of squares is one of them. Ooh, Sam wrote it very nicely on her screen. X squared minus y squared equals to x minus y times x plus y. If you distribute this out at the top, you'll actually find that it's true. So it's a very nice, handy trick to know. And in this case, if we know this is true, we can just expand the top and notice that there's an x minus y in both numerator and denominator. Since we know that x and y are not equal, we can just cancel them out. And we're left with
Also,
x plus
oh,
y.
sorry,
Oh,
Jeff. I
yes,
just wanted
of
to
course.
point out one thing. So Jeff said since x and y are not equal, we can cancel it out. That's important because if x and y are equal, that means our denominator would be zero, and then we'd run into some division by zero errors. So that's why it's really, really important that Jeff in the problem states that x and y are not equal. Okay, sorry. I just wanted to interject that. Jeff, continue. You were on a
Yes,
roll.
that's really, yeah, really important there. We can't divide by zero, big no-no in math. Okay, x plus y equals 100. So the first equation, we simplified by quite a bit. Now, how to simplify the second equation? What do we do here? We get x squared plus y squared over x plus 1 is 36. Do you know a nice simplification for x squared plus y squared? I see Sam shaking her head. I don't either. I don't know how to simplify x squared plus
I
y squared.
accidentally wrote minus.
But maybe there's something we can do about the denominator because we already know x plus y is 100. You get x squared plus y squared over 100 is 36. So x squared plus y squared is 3,600. It's a pretty nice number. How do we find x times y? Do you recognize a nice, like maybe there's like a nice factorization that contains x squared plus y squared? Do you guys know of one?
Well, oh wait. I think I think we can use x plus y whole squared. Now, that's not x squared plus y squared, but it definitely contains that term. So let's take a look at that. We have x plus y whole squared is actually equal to x squared plus 2xy plus y squared. Okay. And we know that x plus y is 100. So this is 100 squared is equal to, oh, and we also know that x squared plus y squared is 3,600. Okay. And we have plus 2xy. Oh, this is really good because what is the question asking us to find, Jeff?
Yeah, the question is asking us to find x times y, and it seems like we have like a linear equation with an x times y in it. Something interesting or something important to note for math competition questions is that often if they ask you for an expression that's not just like x or y, you can avoid finding the individual values within the expression. So notice how we can solve this question without finding x and without finding y and multiplying them together. We can just find x times y together. So Sam, how do we solve your equation?
Yeah, so we could do 100 squared. Well, I don't really want to write out like four zeros. So I'm going to do 100 squared is equal to 36 times 100 plus 2xy. So then I'm going to do 2xy is equal to 100 times 100 minus 36 times 100. And if I divide both sides by 2, I get xy is equal to 100 minus 36 times 100 divided by 2. That was a very bad division sign. Um, and so this 100 minus 36 is 64. And if I divide that by 2, I get 32. So that means x times y is equal to 32 times 100, or 3,200, as Raghuram, Nico, and Ryan, and Bihan, and Cece, and I'm sure so many other people are about to say. So yeah, this is awesome.
Right. I think we're pretty confident with 3,200. Let's turn that confidence into certainty. And the answer is indeed 3,200. Nice. So we were able to save a lot of time by just finding x times y altogether. We're on a roll today. Let's go on to question 17. A plane intersects a cube with side length 6. So the cube has side length 6. The region of the plane inside the cube is shaped like a regular hexagon. What is the area of the perimeter of this hexagon? Ooh,
Oh,
okay.
it says what is the square of the perimeter
Oh,
of the
sorry.
hexagon?
My bad. What is the square of the perimeter? Okay. So I think we find the perimeter and then we square it. Okay, cool. This is some 3D geo here, 3D geometry. And I think we should try to draw a picture. Maybe we can visualize what this looks like.
3D is hard to draw, so I'm gonna try my best.
All right. So with cube,
Oh wait, no, I don't know what I was trying to draw. Oh wait, now I remember. Okay, I was like struggling for a moment there.
and then we have a plane going through the cube, and somehow there's a regular hexagon. Hmm. How do we cut a cube and get a hexagon? Maybe we cut, well, okay, if we cut along like a horizontal, like a vertical cut or a horizontal cut, we know that's not gonna work, right? Because if you cut vertically or horizontally, you end up with either like a triangle or you end up with a rectangle. So that doesn't work. Yeah, okay, so AX said, it has to intersect all of the faces. Um, so sort of like I can like cut into here, and then it'll like go like this, and like, well, it has to be at a sharper angle. Wait, this is kind of hard to think about.
Yeah. Also, since it's regular, that means all the sides and all the angles have to be the same. So that maybe might help us visualize this. Okay. Nico says it would be a weird plane. That's absolutely correct. It's like a really weird like slanted plane like this. So let's see if we can maybe try to draw that.
Okay, I think I kind of have an idea.
Oh my God, wait, that's so good, Jeff. That's
Yeah,
actually a really beautiful
something like
diagram.
that.
I don't know if I can
Okay.
replicate it.
So you enter on like the bottom plane and you go up towards the top plane at like an angle, and then you make like lines here, and then somehow this will work. Its picture looks kind of like this. You have a hexagon. The hexagon exists. You know it's regular too, so that also helps. Okay, I like people. Some people in the chat are saying some people drawing is not very good, but that's okay. It's geometry, not art class. Oh, your picture is really good too, Sam. Okay, nice. How do we start this question? So we have a picture, we have like a general idea of what the picture looks like.
Mine does not look like a regular hexagon, so be wary.
All right, that's okay. We know the angles are all 120, and we know that the side lengths are all the same. Is there a way we can find the side length? So I think the game plan for this question is we should try to find the side length of the hexagon, and then there's a way you can find the area of a hexagon using just the side length. So using that, we can just find the answer, and then, oh, sorry, we're
Oh,
trying to
we
find the
need to
perimeter.
find the area. We
No
just need
area,
to
no
find the
area.
perimeter. So that actually makes our work a lot easier.
Okay, so even easier. We find the perimeter. So we just find the side length, multiply whatever number that is by 6, and then square it, and then we'll be good. Okay, cool. Ooh, so we have some answers too. All right. Um, let's see. A regular hexagon cutting through a plane. Anybody have some ideas? The answers of 648. How are we getting 648? It's a pretty big number.
Okay, so we also have a side length of 6, by the way. Forgot to label that. Oh, okay, so Ryan says we can try some Pythagorean theorem stuff. All right. So I actually want to take a look at one of our faces. So let's say I have a rectangular or a square face actually. So my face looks like this. Wait, I'm just totally drawing over my own face. Let's get some more space. All right. So I've got a space or a face. Gosh, words are hard sometimes. And I've got a side length of 6. So what would my hexagon look like in this case, Jeff? Oh, actually, wait, just kidding. I don't even need to ask you because Rashawn over here is like reading my mind. The vertices of the hexagon is the midpoints of the cube edges. Okay, now, Jeff, what do you think of that? Do you think Rashawn is right?
That seems right. If you imagine all of the faces of this cube, and you think about like looking down on every cube or every square, all of them look like this. There's a square of side length 6, and then you have a kind of like the green line in my picture. It cuts from like midpoint to midpoint. So these are midpoints. And I think we can just find the green length, right? Because we know that this side length is 3, this side length is 3. By Pythagorean theorem, since it's a square, the green length is 3 times the square root of 2. And it seems like that's the side length of the hexagon. Does that seem right to you?
Yeah, I would think so. Um, and since this is the side length, we just need to multiply it by 6 to find the perimeter because this is a regular hexagon. So we would do 3 times the square root of 2 and then multiply that by 6. And that gives us 18 square root 2. And that's our final answer, right? We just put this on the test and we're done.
Ooh, not quite. Notice that it's asking for the square of the perimeter of the hexagon. So we actually have to square 18 root 2. So we can't get too excited and turn in our answer. We have to actually, one more step, 18 root 2 squared, which is kind of a big number. 18 squared is 324. Root 2 squared is 2. So 824 times 2 is indeed 648.
I see, I see. So that is a good reason why you guys should always reread your question and don't put down the wrong answer. Also, it helps to note that the question didn't say to express your answer in like simple radical form. So that means if you're putting a square root down as your answer, you're probably putting down the wrong answer. So just make sure you double check the formatting options because sometimes that actually clues you in onto what your answer looks like.
Yeah, I definitely agree with that statement. Hate to admit it, but I think I've gotten many questions wrong in the past because I've not I did not answer the correct question.
Oh
Okay.
yeah.
Yes, like Albert says, underline stuff or highlight. Yeah, I actually find when you're reading through the question the first time, highlight important info. Like highlight places where you could make mistakes. So when you look back later, you'll be like, oh, it says square, not just the perimeter. All right. Are you ready for the next one?
Yeah.
All right, let's check our answer first. It's indeed 648. Wow, we are on a roll today. Gotten all of them right so far. Let's keep it up with question number 19.
Okay, so we've got a non-zero real number, and we have x squared minus 7x plus 1 is equal to 0. And we want to find x cubed plus 1 over x cubed. Oh my goodness, that's so weird. Why are we looking at cubes when we already have a quadratic? Jeff, what do you think we could do? I'm just so confuzzled. Oh my goodness.
Hmm. Well, I mean, we could find x, right? If we're trying to find this expression, we could find x with quadratic formula. So that would work. Unfortunately, we don't really want to solve that quadratic because you're going to get, like, if we do b squared minus 4ac here, you immediately get some very ugly radical. And then you have to cube it and then take 1 over the cube. And then that's not really something I want to do on a test exactly. So maybe there's a nice way we can solve this question. And I'll just say for this question, this is one of those questions where like when you see the solution one time, you'll never forget the solution. But if you've never seen the solution before, it's very challenging.
Yeah, I totally agree. I mean, the first time I saw a question like this, I was just like, I was like, cubes in a quadratic, like, what is happening here? But there's definitely some tools that we can use to solve this. So, I see lots of people saying, oh wait, hold on. Actually, just kidding. Oh, okay. So I see lots of people isolating some variables and things. So let's see if we can do something like that. Can we isolate any variables in this case?
Hmm. Let's see. So we're trying to find x cubed plus 1 over x cubed. We have some squares. In general, for this question, it helps to divide across the quadratic by x. That's something we never actually do that when we're solving quadratic, so it's kind of weird. But trust me, it works here. So you get x minus 7 plus 1 over x equals 0. And if you add 7 to both sides, you get x plus 1 over x equals 7. So this looks pretty similar to x cubed plus 1 over x cubed. It seems like we have to just like modify this a little bit, and then you could get the answer.
Yeah, I agree. I agree actually. So let's you know what we since we're working in the realm of cubes, I really think we should cube this x plus 1 over x expression. So let's go ahead and do that. Let's go ahead and take a look at what it would look like to cube this algebraic expression. Now, if you've never seen how to sum a binomial, or that's not what I'm trying to say, how to cube a binomial, we're gonna work through this step by step. And so what we first start off with is just x cubed. We just go with x cubed, and then we add 3 times of x squared times 1 over x, and then 3 times x times 1 over x squared, and then plus 1 over x cubed. Now, there's lots of beautiful patterns in where this expansion comes from. Namely, if you look at the coefficients or if you look at the exponents, lots of really cool things there. Jeff actually is putting up kind of where some of this stuff comes from. So, Jeff, if you want to go ahead and explain that, that'd be really cool.
Yeah, so this is binomial theorem. Um, you might not have heard of it before, but it's a really nice way that you can expand the binomial that we have. Binomial just means that it's something in the form of like a plus b to some power like n. That's binomial. And the expansion is it's like a to the n. So in this case, a would be x and b is 1 over x. It's like for the first term, x cubed times 3 choose 0, and then x squared times 1 over x times 3 choose 1, and then 3 choose 2, 3 choose 3 are the coefficients. So the pattern is the power of x is decreasing as you go down, and the powers of 1 over x are increasing as you go down. And the choose functions, it's like 3, which is the power. It's the power choose 0, power choose 1, power choose 2, and so on. Binomial theorem is something, it's pretty advanced. But in fact, if you want to do the question like a different way, expand a different way, you could just expand with distributive property, just do x plus 1 over x and multiply by itself 3 times. In fact, actually, normally when I do expansions, I do that a lot as well. In this case, it's only 3, so it's pretty easy. And if we simplify this, you get x cubed plus 3x squared, 3x squared times 1 over x, which is 3x, plus 3 times 1 over x, plus 1 over x cubed. So we have the parts we're looking for. We're just trying to get rid of this 3x plus 3 over x in the middle. How can we do that?
Yeah, so we can actually factor out that 3 from that weird middle portion, and we get 3 times x plus 1 over x. And hey, would you look at that? We've got x plus 1 over x, and we already know that that's 7. So we're basically having x cubed plus 1 over x cubed plus 3 times 7, which is 21. And that total value is equal to 7 cubed. So our final expression is actually going to be 7 cubed is equal to x cubed plus 1 over x cubed plus 3 times 7. Or that's 343, which is 7 cubed. If you don't know that 7 cubed is 343, that's totally okay. You can do 7 squared is 49 times 7 and find that it's 343. And then that is equal to x cubed plus 1 over x cubed plus 21. So x cubed plus 1 over x cubed is equal to 343 minus 21, which is 322, as so many of you guys are saying in chat. And that seems like our final answer. Let's take a look.
Yeah, so the trick to this question, kind of like the last one, is you don't have to actually individually find x. You don't want to find x actually, because we tried finding x. It didn't really go so well. The trick is you write x plus 1 over x because it's easy to do with a quadratic, and we use that expression, do some tricks with it, and we get our final answer, 322. Cool. All right, ready to check, Sam?
Yeah. Oh wait, I was so off cue. Okay, there we go. 322. Awesome. Okay, you guys are doing really great today. But we are actually hitting our ending time. So it is 7:58, and I don't know if we have time for another question since this next question seems pretty difficult. So Jeff, are you okay with ending here?
Yeah. Although if chat wants to go on one more question, we can do that as well. We have 2 minutes, so maybe we could you want to try to speed run the next question?
Okay, yes, let's do one last question. All right, we'll end on this
All
last
right,
question.
let's solve this one really quickly. Okay.
Yes.
What is the remainder when the sum of the first 2025 positive perfect squares is divided by 100? Oh man, okay. This is a big number actually. The sum of the first 2025 perfect squares, that's like what? That's like 1 squared plus 2 squared, and then that's like up to 2025 squared. Oh man, I don't know what 2025 squared is. So this is pretty challenging. I see people say formulas in chat. Any ideas for a formula, Sam?
Yeah, so there is actually a sum of the squares formula, and that is probably the best way to approach this question, in my opinion. So in one of our live classes, we actually do work with a proof, and we kind of look at like why the sum of the squares formula works. Unfortunately, today we just don't have the time to cover that. So we're going to show you guys the formula, and then we will solve the rest of the question. And if you guys are interested in where the formula comes from, definitely look it up because it's an approachable proof. You guys could definitely see what it looks like. Okay, so Jeff already has on his screen that the sum of the squares is, hold on, I'm very slow at writing, n times n plus 1 times 2n plus 1 over 6, where n is the last number that we squared. So Jeff, how can we use this to find our answer?
Well, let's plug in the number we're trying to find first. We're doing 2025 by 2026 times, this is 40, 40. or sorry, 4051, all divided by 6. Okay, so this is kind of a big number, but they're not asking for the whole thing. They're only asking for the when the remainder when you divide by 100. So the remainder when you divide by 10 is a unit digit. The remainder when you divide by 100 is just the last two digits. So what is the last two digits of this number? So right off the bat, we can try to get rid of the 6 in the denominator. 2026 over 6, is this divisible? This is not divisible by 3. What about 20 or 4051? Oh, that's also not divisible by 3, but we know 2025 is. What is 2025 over 3? Hmm. Well, this is like, we could probably just do some division here. 6, 18,
I see a lot of
24.
people saying 675. Jeff, is that what you're getting to?
Yeah, that's what I'm getting. That seems right.
Okay,
670.
awesome.
Okay, so 675. And then we can also get rid of one of the twos here. Let's just get rid of it here. This is 1013.
Okay,
Cool.
so now we have 675 times 1013 times 4051. And since we're only looking for the remainder when divided by 100, we're looking at mod 100. We only care about the last two digits. So essentially, we want to find the last two digits of the product 75 times 13 times 51. So Jeff, how can we do that?
Well, my first instinct is we can probably just do it. Like
Yeah,
this is not too hard of a multiplication, right?
yeah,
We can
I
try to think
agree.
of a trick. But like sometimes in math, it's like a balance between, okay, the computation is too hard. There must be a trick versus if you spend time thinking of a trick, maybe the intended solution is just computation. Like maybe we could spend the next couple minutes trying to find a neat solution, but by that time we've already bashed it out. So let's just try to bash it out. I think shouldn't take too long. Let's just start with, let's just pick two of them to start with. 75 by 13. 75 times 13. Let's multiply.
Actually, really quick, before we bash out 75 times 13, I think it's worth noting that 75 times 4 is 300. So that actually greatly simplifies our computation because now we're ending with some zeros. So can we use this, Jeff?
Yeah, I actually think so. So maybe instead of doing it this way, that's a very cool way we can simplify this. So 75 times 12, because 12 is a multiple of 4 plus 1. This is 75 by 12. That just ends with two zeros because we know 75 by 4 is 300. So this is just 75 again. This should end with the digit 75. So now it's 75 by 51. Let's try to use the exact same trick again. So this is 51 over 4. The closest multiple of 4 is 48. So it's like 48 plus 3. So 75 by 48, that also ends with 0. We only need 75 over times 3. 75 times 3, you can write it out. I think it's 225, if I'm not mistaken. So
I
the
think so
final
too.
digits should just be 25. 25.
And that is math on speed run. Okay, let's see if our answer is correct because we totally like went through that super duper fast. Alrighty. We are correct. Oh my goodness. Okay, so that was like really, really fast. If you guys didn't get that at all, which is totally understandable, definitely go check out this live stream once again. It'll be posted on YouTube and try to work out through the little steps, that computation, those answers, kind of the random stuff that we skipped over, because I really think you'll find that this is a really interesting solution. Okay, awesome. So I know we didn't get through all the questions and we didn't really look at the target, but since we are over the 8 o'clock mark, we're going to go ahead and end now. For those of you guys waiting to get to that Super Bowl halftime, you guys can make it. I'm about to head over to my friend's house to check that out. But yeah, thank you guys so much for being here tonight. We really, really enjoyed having you. You guys have been a really great interactive audience, and hopefully you learned how to solve a couple of these Mathly questions. Jeff, you got anything to add?
No, that was a perfect ending. Thank you all for coming. I hope you have a great night. And if you don't have anything else, Sam, let's call it a night here. Thank you
Okay,
guys.
awesome. All right, bye, you guys. Thank you so much for joining us. We were so lucky to have you here today with us. Bye, everyone.
Bye. Oh, CC, 50 stars. That's very impressive. All right.